This morning, our podcast passed an important milestone. We passed 1,000 downloads. We know that means you're watching, but almost no one is participating in the discussions. Please check out the website and give us your feedback. We would love to hear from you. And thanks for watching. At any one time, there can be up to 5,000 planes flying over the United States airspace and hundreds more taxiing on runways. The FAA controls a total of 87,000 flights every day. The air traffic control system keeps track of all of that traffic to ensure the safety of all of the planes. That system contains a significant amount of technology and some very interesting software applications.
The air traffic control system is divided into two parts: tracking planes on the ground and tracking planes in the air. When planes are landing, taking off, or taxiing on a runway, they follow instructions provided by controllers in airport control towers. When a plane is in the air, there is a regional air traffic control center that is tracking its position and altitude and directing it so that no plane flies within 5 nautical miles of any other plane. While in the air, controllers will direct planes not only around each other but also around weather patterns that might make the flight uncomfortable. As a plane flies across the country, one of the challenges the technology has to deal with is handing control of the plane from one regional control center to another. This must be done carefully so that no plane is ever uncontrolled. Therefore, the ground centers and the pilot must all communicate to make that transition. As we look at the technology behind this system, this is one of the problems that we will look at carefully.
The first problem to address in keeping planes safe is knowing exactly where every plane is at all times. One way the air traffic control system tracks the position of planes is with radar. There are two types of radar. The primary radar is based on reflecting sound waves, similar to the echolocation used by bats. Signals are bounced off the aircraft, and their direction and distance from the radar station can be measured. In addition to the primary radar system, there is a secondary radar system. The aircraft must be equipped with a transponder. When an aircraft detects a ground radar interrogation, it responds with its own identity and other information, which includes exact location, altitude, heading, and speed. While that link is a radio link, the communication is encoded, much like the zip codes we talked about a few episodes ago, to ensure that the messages are received without error.
For many years, the controllers on the ground have been able to communicate with pilots using two-way FM radios. With this radio communication, the controller and the pilot must be tuned to the same radio frequency. There are a number of limitations to this technology, however. First, there are a limited number of frequencies, and pilots have to listen to all transmissions on their frequency, so the busier the airspace, the busier the frequency. Pilots can be distracted by listening to too many conversations. Second, this type of communication can be noisy, can be disrupted by things like sunspots, and can be further confused by accents of foreign pilots. To help prevent miscommunication, every instruction from the controller to the pilot must be repeated by the pilot to the controller. However, this uses even more airtime on the frequency. Finally, passing a plane from one region to another requires a change in frequency. If there is a miscommunication at that point, the pilot must be using one frequency while the regional control center is using another, and communication with the plane is lost. New digital technologies are giving controllers and pilots much better communication capabilities. Essentially, software engineers have used digital radio links to eliminate many of the existing communication problems. One example of this new technology is called Aircraft Communications Addressing and Reporting System, which is shortened to ACARS, and allows the controllers to communicate with pilots using text messages instead of voice communications. Essentially, with this, the way they communicate is much like instant messaging. Since the communication is in text-based messages, much of the confusion of voice communication has been eliminated, so the messages do not have to be repeated anymore. In addition, since this isn't person-to-person communication, The pilots or controller can complete other tasks before responding to a message. This greatly improves the quality of the communication and saves the pilot and the controller a significant amount of time.
While ACARS significantly improves communication, software engineers have used this ground-to-plane communication to provide other communication and to automate some tasks for the pilot. Remember that as planes travel across the country, they have to be passed from one ground control center to another. Software engineers have developed software that automates that transition using ACARS communication. With this new software, communication with the plane cannot be lost during that transition. ACARS is also used to give the pilots more information related to the flight. The pilot can request information from automated systems on the ground for information such as weather and stored departure clearances. ACARS also connects the cockpit to the airline's host computer systems. The large flight displays in airports which show the on-time status are fed using this information. The airlines also have software which uses ACAR flight status to update flight status on the airline's website. In addition to automating some of the communication between the ground and the plane, software engineers have made ACARS automate things for the pilot. In particular, when the controller sends new flight path instructions to the pilot, ACARS can automatically load those instructions into the plane's autopilot computer. This allows the pilot to focus on other tasks instead of hand entering data into the autopilot computer. This also eliminates human error that could result from hand entering the data.
You can see that the air traffic control system contains a lot of software, and we've only been able to talk about a small portion of the interesting problems that software engineers are working on. One of the significant challenges that software engineers have to deal with in this situation is that the timeliness of a response by the computer matters. When you're surfing the web, a slow response time is annoying, but not really damaging. However, when you are directing an aircraft traveling at 2/3 the speed of sound, time is crucial. A 20-second message delay means the aircraft has traveled over 2 miles between the message being sent and received. In computer science, we call systems with these time requirements real-time systems, and we develop specific strategies for ensuring that the right behavior happens at the right time.